Hello, thank you for watching this video. My name is Radu and I will tell you about some work I did with Shin, Ravi and Mayur from Georgia Tech and Hongseok from Oxford. This is an example of a static analysis. What we're trying to do is keep track of whether files are open or closed. On the right hand side in the comments, we see that the static analyzer can figure out that at the end of this small program the variable x points to an object that corresponds to a closed file. In a big program, we might want to track only a subset of the variables, not all of them. For efficiency reasons, it might be too slow to track everything. The side effect of that would be that we will be able to infer only a subset of the things that we were able to infer before. In this particular example, if we track only the variable x, for example, we will not be able to tell that at the end of this small program x points to some object that corresponds to a closed file. The reason is the following. When you track only a subset of the variables, then you need to have some notion of untracked variable. In the state that the static analyzer is tracking and appears on the right, untracked variable is represented by a star. So after the assignment y equals x, the state of the static analyzer is that x together with some untracked variables are pointing to an object that represents an open file. Then when we see that some untracked variable is closing, it is calling this close operation, we know that anything that could be aliased with an untracked variable might or might not go from the state open to the state closed, because there's not one single untracked variable, there's several of them, and we don't know which one we called the action close. So we know that y is untracked when we see y.close. We know that x is aliased with some untracked variable, but we don't know that it's the same, that it's y, because we're not tracking it. So we say, well, from now on we don't know whether the object to which x points is open or closed. So when we get to the end, we just don't know what the state is. The parameters of this static analyzer are the program variables. For each program variable, we assign a value 0 meaning do not track and 1 meaning do track. The abstraction is this assignment of booleans to program variables. The family of abstraction is finite. There's only a finite number of possible abstractions because there's a finite number of program variables and it can take values from the set 0, 1. But in some situations the abstraction comes from an infinite family, and this is what the second example illustrates. In this example we are interested in whether the arguments of the function c are aliased or not, and the answer is of course that it depends from where the function c is called. When it's called from a, the assertion is not violated. The two variables x and y do point to different objects, but if c is called from b, then the assertion is violated. So whether the assertion is violated or not depends on the context. But when we run a static analyzer that does aliasing analysis and keeps track of context like this, of who called who, we need to be careful because these contexts are lists that can grow arbitrarily long. So if we want to ensure that the analyzer terminates, we need to truncate them. And that brings us to what an abstraction is in this for this kind of analysis. The parameters of this analyzer are function names, are the functions. For each function we associate a value, but this time the value is some non-negative integer not necessarily 0 or 1. It could be any other integer. If we associate, for example, the value 3 to the function c, that means whenever we get to with the analysis to the function c, we're going to truncate the context to length 3 if it happens to be longer. If we associate the value 2 to function b, then when we get with the analysis to the function b, we truncate the context to length 2, and so on. This assignment from functions to maximum context lengths is the abstraction in this case, and there's an infinite number of possible abstractions because the values that we associate to parameters are natural numbers. There's one more thing that could happen. If we happen to choose an abstraction that says for all functions truncate the context to length 1, well, then we don't know if the assertion fails, because when you get with the analysis to function c, we just don't know who called it. We're not keeping track of that. We truncate the context to length 1, we just know we are in c, but we don't know who called c. We forgot that. That's what the parameters of the analysis tell us, if they are all 1. So we don't know if the assertion fails. But if we want to implement the static analyzer so that it is sound, then it will stay on the safe side and say, well, it may fail. So if you're asking if something bad may happen, then I say yes, something bad may happen. Whereas if we have context of length 2, then it knows for sure that something bad will happen when c is called from b. Well, in general, the setting is the following. We have an analyzer, a static analyzer, that reads a program, a query, and an abstraction. And it says, yes, something bad may happen relative to the query, or no, something bad cannot happen. And what we're interested in is to find out if there exists some abstraction for which the answer is no, in which case we're happy, or the analyzer will say yes for all possible abstractions. In the previous example, no matter how it truncates the context, the analyzer is going to say yes, something bad may happen. What I'm going to do next is rephrase this problem, but in a more formal setting. So I'm going to say exactly the same thing as I said until now, but in a more precise way. To do that, I need some notations, and that's what this slide introduces. I referred so far to parameters. From now on, I'm going to identify parameters with the integers 0, 1, 2 up to n minus 1. Abstractions assign integers to parameters, and we're also going to have Boolean assignments, to which I'm going to refer using the name parameter masks sometimes because of how they are used. And finally, there's 3 more concepts that are going to be detailed on the next slide. F standing for the analysis, G of X for the local provenance at some particular abstraction, and H the global provenance. Okay, this slide tells us what assumptions we make on the analysis, the local provenance, and the global provenance. The first 3 lines give us the types of these functions. Maybe a few more words about notation. N stands for the set of integers 0, 1 up to n minus 1, like in set theory, and omega stands for the set of natural numbers. 2 stands for the set of booleans 0, 1. So the analysis is simply something that takes an abstraction, which is a function from n to omega, and returns a boolean. So an abstraction is something that associates a value to each parameter. So abstractions belong to the set n arrow omega. If we give the analysis f an abstraction, it gives us back a boolean, the answer yes, no, that we saw on the previous slide. We are concerned with this search problem. We try to find some abstraction for which this f is going to return 0, no. But if we don't know anything more about f, then it's kind of hard to do better than exhaustive search. So we're gonna open up a little bit this black box, and that's what the local provenance g does. So g is a function to which you give an abstraction, and it gives you back a boolean function. This boolean function takes a parameter mask and returns a boolean. It basically means, what if I use only these parameters to do the analysis? Just ignore everything about the other parameters. What would be the answer? That's what G means intuitively. The relation between f and g is given by the global provenance h. If you look at the type of h, you see that it takes a function and returns a boolean. The function that it takes is something to which you give a parameter, a value, and it tells you whether the parameter has that value. So h is given a function that it can use as follows. It says, does parameter 2 have value 4? And this function says yes, or it says no. And h uses this answer to compute its result, the result of the analysis. So how do we define f in terms of h? Well, we simply ship a function which checks if the value of the parameter is the one that the abstraction says should be. So when h will ask, does parameter I have value k? Well, we say, well, let's ask x. What value the parameter I should have, and it says, well, it should have the value x of I. Is that the same as k? If it is, we return yes, otherwise we return no. And g of x and the local provenance g is defined in a very similar way, except you also get this parameter mask, and you return yes if the parameter has the value it's supposed to have and the mask says you are allowed to use that parameter, otherwise you return false. So f and g are related by how they are defined in terms of some function h. We make two more assumptions. These are monotonicity assumptions. We assume that the analysis f is anti-monotonic. What does this mean? It means that if we increase the values of some parameters, and therefore increase the precision of the analyzer, the only way to change the answer, so the static analyzer could only change its answer from yes, something bad could happen, to no, something bad cannot happen. And that's if the previous yes answer was because the approximation was too coarse, and now we gain precision and we give a better answer. It never happens that you give the answer no, something bad cannot happen, then you increase precision, and now it says, oh, actually, you know what, something bad could happen. So that doesn't happen. This is what the anti-monotonicity of the analysis means. And we also assume that the global provenance H is monotonic. That restricts a little bit how the analyzers can be implemented. And this is discussed in the paper. Now notice that in these lines that introduce anti-monotonicity and monotonicity, the last two lines on the slide, I use the sign less than or equal between functions. X and Y are abstractions, so they are functions from n to omega. What I mean by that is the pointwise order. I mean that for each parameter, the a value given by the abstraction x is at most a value given by the abstraction y. Okay, now using only these simple assumptions, we can already find some interesting, prove some interesting results. For example, I said that this local provenance gives us more information than the analysis. We should maybe make sure that we have at least as much information as the analysis. And that's very easy to check. We just apply the local provenance at x, that is g of x, to the constant function 1, so the parameter mask that says use all parameters. And this proof, in the first step, it unfolds the definition of g. Then in the second step, what it does is that it applies this constant function 1 to I. The result is going to be 1, which is the identity of conjunction, so this second conjunct disappears. And in the last step of the proof, we fold back the definition of f. So if we know the local provenance of at x, we know the result of the analysis at x. Another result is about the monotonicity of G. I said that the analysis F is antimonotonic, assumed to be antimonotonic. The global provenance H is assumed to be monotonic. I didn't say anything about the monotonicity of local provenances, but it can be shown that they must be monotonic. So in this proof you see that on the first line we unfold the definition of G. In the second step of the proof we use the hypothesis, and in the last step of the proof we fold back the definition of G. So assuming that U is at most V, we deduced that G of X is at G of X of U is at most G of X of V, and therefore G of X, and that's the definition of monotonicity for G of X. The second step of this proof is maybe hard to follow if I go over it so quickly, so I want to spell it out on this slide. The only maybe thing that you should know about this slide is that for lack of space I wrote this B in blue for the expression that appears in blue on the fourth row, and the same with C. It stands for the green expression on the fourth row. So wherever you see B, imagine the blue expression that you see on the fourth row. Wherever you see C, imagine the green expression on the fourth row. The first step of this proof says, because H is monotonic, if we want to prove that H applied to something is at most H applied to something else, it is sufficient to focus on the arguments. The second step of the proof says we're comparing two functions, and when we're comparing two functions, the order that we have in mind is the pointwise order. So we unfold the definition of pointwise order. That means that for all I, k, b is at most c. Then the third step, we eliminate the quantifiers. The fourth step says, well, we have a conjunction of the left, a conjunction on the right. X of I equals k appears on both sides. We can see you can think of this conjunction as a minimum operator. So if x of I equals k is true, then we just have to show that u of I is at most v of I. If x of I equals k is false, then everything is fine. So it is sufficient to show that u of I is at most v of I. And this next step, we introduce the quantifier I. Then we use the definition of ordering pointwise order of functions, and then we just say, well, lambda I u applied to I is the same as u if you use Leibniz extensionality. So now if you read the proof, if you read the last line of the proof, it says that if u is at most v, then, and now we read the first line of the proof, h applied to some lambda is at most h applied to some other lambda. And that's what we had here in the second step of the proof. h applied to some lambda is at most h applied to some other lambda under the hypothesis that u is at most v. So this is that second part of the proof spelled out. So far we showed that the local provenance at an abstraction X contains at least as much information as the analysis at abstraction X. That local provenance must be monotone. And now a more interesting result is this prediction lemma. Remember that what we're trying to do is to search for an abstraction. We would like to do so without actually trying all the abstractions. So we want to prune this search space without looking, without actually running the analyzer on all the abstractions. And this prediction lemma lets us do this on the basis of the local provenance. What it says is this: suppose you have the local provenance at y, so we have g of y, and suppose you apply it to some parameter mask u, and the result you get is 1. Well, this lemma says that g of y of u is at most f of x. So if g of y of u is 1, then it must be that f of x is also 1. So knowing the local provenance at y gives us the value y with some mask u, we can predict that the analysis at some other abstraction x will return 1 without actually trying it. And the condition that has to be satisfied is that this mask has it keeps only parameters whose values agree in the abstraction x and in the abstraction y. Now this constraint could seem a little bit too strong because it says the x and y abstractions should have some parameters where the values agree exactly, but you can combine this prediction lemma with the anti-monotonicity of f. So if the prediction lemma gives you that some x is gonna make the analysis return 1, then you also know that all the smaller abstractions are gonna return 1. So and those do not necessarily have to agree with the abstraction y for which we have the local provenance, and that prunes out even more of the search space. So here's one example of how to use this. It might be that the local provenance you get back is a tautology. Since g of y is a monotone function, you can tell it's a tautology by just evaluating it for the constant function 0. And if it says true, then you know that it's a tautology. In that case, you know that the analysis will return 1 for all abstractions. So to give you an example, think back about the calling context example. In that situation, say you first use an abstraction that says truncate all calling context for all functions to length 1. And the result that you get back is going to be, well, yes, something bad can happen, may happen, and some local provenance. Then you analyze the local provenance, you think about what you try next, and you say, okay, now let's try to truncate all contexts for all functions to length 2, let's say. Well, what you get back now is again the answer yes, something bad may happen, but you also get a local provenance which will be a tautology. And because that's a tautology, you can tell that no matter what other abstraction you will try, the result is going to be yes, something bad may happen. So that's how this corollary is applied for the example with calling context. You're going to get a tautology when exactly in those cases when you know for sure that something bad can happen. And it's not just because you're staying on the safe side to be sound. Okay, so far I lied a little bit. I said that the local provenance at a certain abstraction is some Boolean function. But in fact, in our implementation, where the static analyses are implemented in Datalog, what we get back is a set of constraints that look like horn clauses. So on this slide, alpha is what I called so far a local provenance at a particular abstraction, and beta is this set of constraints that we actually get back. The equation that you see on the slide is how these two are related. So you can see the local provenance as being a Boolean function that is defined in a particular way in terms of some constraints that I'm going to call beta. And one of the assumptions we made earlier was that these local provenances must be monotonic. But what we get back is this constraints. So let's see, if we want the local provenances to be monotonic, how should these constraints look like? This is the question that I'm asking on this slide. To answer it, I'm going to do a little bit of manipulation. So first I negate both sides, then I expand this quantifier, and now I'm going to think about this last equation in more semantic terms. So let's see what it means. We want alpha to be monotonic, which is the same as saying that we want not alpha to be anti-monotonic. What does it mean that the Boolean function is anti-monotonic? Well, you can think of it in terms of this Boolean assignment. So u is a Boolean assignment. We can write it down as a bit vector. If not alpha of u returns true, returns 1, we say that this assignment is a model of not alpha. Now we pick some bit in this bit vector and we change it to 0. What we get back is another bit vector which could be a model of not alpha or not. If it always happens that it's a model of not alpha, then that's basically the definition of anti-monotonicity. So if it always happens, no matter with which model you start and which vector you pick to reset, that you end up with a model, and that's anti-monotonicity. So on the left hand side we have that we have this bit vector, we reset a bit, and if we started with a model we end up with a model. Now on the right hand side, if we mirror this operation, what we get is that there's a bigger bit vector that has a part called u and a part called w. In the part called u we reset some bit, and now if we want to the whole right hand side to still evaluate 1, that means that we should be able to find some w extension of the u part that satisfies b, that gives us a model of beta. So we started with some u and some w that we plugged into beta, and it returned 1. Now we changed one of the bits in the u part by resetting it, and we are allowed to reshuffle completely the w part to get a model. So this suggests a natural sufficient condition for beta that will ensure that not alpha is anti-monotonic. We might just insist that this w part we can always keep the same thing. So we don't know if so we just insist that beta satisfies this condition. If we take a bit in the u part and reset it, we get another model. And that means we just say, well, you can use the same w. you don't need to change it. So that's a sufficient condition, not a necessary one. And we can phrase it like this. We say if beta is anti-monotonic in the U part, then alpha is monotonic. Let's look at an example. So if beta is a conjunction of these constraints, which are Horn clauses, they are implications, there's no negation, we can immediately tell that beta is anti-monotonic in U because the U parts occur only in negative positions. They are only on the left hand side of implications. They are never on the right hand side. And that immediately tells us that beta is anti-monotonic. So according to what we saw on the previous slide, it must be that the alpha defined in terms of this beta must be monotonic. And on this simple example we can check whether this is true or not. So I claim in this slide that 0, 1 is a model of alpha. Let's see how we check this. Well, 0, 1 means u of 0 is 0 and u of 1 is 1. So we plug in the value 1 for u of 1 in the second implication. That tells us that w of 1 should be 1. Then the second to last implication tells us that w of 0 should also be 1. At this point we know that w of 0 and w of 1 are both 1, so the last implication tells us that q must be 1. So what did we do? We said we plug in the values for u, we do only what we're forced to do such that beta holds, and we concluded that q holds. But that's exactly the definition of alpha. It says no matter what you try, if beta holds then q holds. So if that's the case, then alpha holds. So we show that that is the case, and therefore alpha of 0, 1 evaluates to true. And you can do the same for the other assignments, and now looking at them we can check that it's monotonic. So if we start with 0, 1, for example, if we set a bit to 1, no matter which one, the first one or the second one, we get another model. Okay, so now I presented enough background to tell you what we're doing in the paper. In the paper we do this, we solve this refinement problem. We say, given few sets of constraints, beta 1 to beta k, so several sets of constraints, each of them representing local provenance at some abstraction. So beta 1 represents alpha 1, which is the local provenance at some abstraction x1, and so on. So given this, we want to find some abstraction x for which the prediction lemma, together with the anti-monotonicity of f, does not imply that the analysis will return yes, something bad may happen. So using these constraint sets, we look at the search space, we prune out everything that we can using the prediction lemma and the anti-monotonicity of f, and then we want to pick some abstraction from what remains from the space, from the abstractions that remain after we carved this out according to the prediction lemma and anti-monotonicity. And out of the abstractions that remain, we will pick one that is cheapest in terms of some heuristic cost. And that's why this turns out to be an optimization problem, which is naturally expressed as a max-sat problem. Now there's a lot of related work. I'm gonna emphasize here maybe just two. So I said that the implementation ends up being Datalog implementation of a static analysis, then refinement based on a max-sat solver, and then repeat. There is this iteration loop. The Datalog solver that you use in the implementation is BDD-BDDB, and it is described in the paper from 2005. The max-sat solver that you use is a lot more recent, from 2013. It's called the MIFO-Max, and it's a literate solver, so its source code is a little bit like an article, reads a little bit like an article. Apart from the articles that are on this slide, there's a bunch of other closely related works. For example, Corneliu Popea and Andrei Rybalchenko and others looked at horn clauses and trying to solve them, and the horn clauses they look at are in similar context, and by context I mean the quantifiers that you put in front of them, and they have some papers on how to solve this kind of problems using some, for example, template based methods. And there's some other stuff out there as well. Now, if you're a bit curious, if I made you a bit curious, what I recommend is that you look at this paper that appeared in PLDA on abstraction refinement for static analysis in Datalog. You'll see there some explanations of why the assumptions that I made in these slides are make sense. You'll see that you don't always need to make all these assumptions, but the experimental results, so the experiments that we run do obey the assumptions that I used in this presentation. And the nice thing is that the experimental results are actually quite good. I think, well, at least I was surprised. I think my colleagues are also surprised about how well it works and how well it scales to large programs, and it goes to, so it bumps up the value of parameters quite a lot, so it's really good. The implementation is open source, based on Google code in this project called JCord that Mayur started a long time ago. I think that's it. I think that by making this presentation I learned a bit better what we're doing in these papers.